Yes, yes.
Excellent. So our next speaker is Gábor Somlai from Budapest, who talks on Fuglde's conjecture, the one-dimensional case. Please.
Okay, so first of all, I would like to say thank you for having me here. And I have to mention that I'm not the only one who is going to talk about Fuglde's conjecture. So Gergely Kis will talk about it tomorrow from another perspective, and he's obviously one of my co-authors. But there are two other people who I wrote papers together on this topic, and they are Romanos Diogenes Malikiosis and Máté Vizer. So it's worth mentioning their name. So let me just start directly with Fuglde's conjecture. So Fuglde's conjecture says that so you can say it, and you can define it on locally complex groups. So measurable subset of locally complex group is a tile if and only if it is spectral. But obviously I have to define what I mean by a tile, or what it means to be spectral. So a subset is a tile if it almost translates covered the group. So it means that you can have holes of measure 0, or you could have overlaps of measure 0 again. And T is spectral if you take the set of L2 functions, and then it is spanned by the restrictions of exponential functions, which are pairwise orthogonal. So the restrictions should be pairwise orthogonal, and not the exponential functions themselves. And most people investigate the case of the Euclidean space, and which has strong direction with the case of finite abelian groups. So I'm going to move to the case of finite abelian groups, or I'm going to talk about them a little bit. So first of all, it's easier to talk about finite abelian groups because there is no need to talk about sets of measure 0 in this case. So if you have a tile, then you will cover everything once, and all the functions are L2 functions. So it's not again, it's not a restriction. And I'm going to talk about this a little bit later again. So exponential functions are just parameterized by the elements of the original group G. So you can think of them, so a subset of exponential functions will be just a subset of the group G. So you could talk about spectral pairs where this is a set and this is its spectrum, and the role of these two things are symmetric. So both of them are in G, and we will be able to use the fact that if T lambda is a spectral pair, which is not properly defined yet, then lambda T will also be a spectral set. And obviously the cardinality of these two sets will be the same. And yeah, so we will talk about two different directions of the conjecture. So the tile spectral direction, the spectral tile direction of the conjecture. So exists. But I will mostly concentrate on the methods developed for the spectral tile direction, and not especially. So I will talk about the results as well, obviously. So again, I mentioned that there is a strong connection between the case of the finite and the infinite case, more precisely the case of the group R, Z, and this symbolizes just the O cyclic of O finite cyclic, in the case of the O finite cyclic group. So this is the symbol for an infinite class of groups of the finite cyclic groups. And this says that so this is a theorem of Dudkai of Lai, who proved that the tile spectral direction of the conjecture on R is actually equivalent of the tile spectral direction on N, and this is equivalent to the tile spectral direction of the conjecture on every finite cyclic groups. So the spectral tile direction is, so we have weaker results. So we don't know, so we know that the spectral tile direction on R, so if it is true, then it implies that it is true on Z, and it is true that then it implies it is true on every finite cyclic groups. So if you want to have a counterexample, then you could try to look for that here, but we don't know yet whether the reverse implications are true or not. So okay, so let me go back to the original conjecture. So the conjecture was disproved by Tao. So his observation is the following. So it's not easy. So but I'm not going to explain it. Probably Gergely will explain it tomorrow. But it's not really hard to find a spectral subset in Z3 to the 5 of psi 6. So, which is spectral, but this is not a tile. So it's a group whose order is a power of 3. And if you have a subset of psi 6, then since 6 does not divide 3 to the 5, then it's not a tile. So it's so this part is easy. Proving that the spectral is not much more difficult, but you need to have a really nice idea for that. Okay, so Tao used this observation in order to disprove the conjecture in the 5-dimensional Euclidean space. So he lifted up the construction of for this finite group to the Euclidean space. So this disproved the conjecture in the 5-dimensional case, and this was reduced to the 3-dimensional Euclidean space. So both directions are disproved of the conjecture, and this is the work of Koluntzakis, Matolcsi, and Matolcsi, and Farkas, Móra, and Matolcsi. So okay, so what are the currently best available results for cyclic groups? So on the top you can see the spectral tile direction, and on the bottom the tile spectral direction, and so in general you can see that, okay, so you can compare them. So this is the case of when you have two different prime divisors. So P, Q, R, and S are different primes in this case. And for the spectral tile directions, as you can see, there are some conditions, some very strong conditions on M and N. And in the case of the tile spectral direction, which is a result of Laba, so the conjecture holds. Okay, so the conjecture holds for all these groups. So the tile spectral direction. So you don't have restrictions on the exponent here. So it's somewhat stronger. And if you compare the last result, then you could see that there is a slightly stronger result for the tile spectral direction. And in the middle, you can see two results. So this one is stronger than the previous one, but this is way weaker than what we have for the tile spectral direction in this case. So that's currently where we have. So actually, the Fuglde's conjecture is proved for, I don't know, so for the case of when the order of the cyclic group is just divisible by at most 4 primes. They don't need to be different. So if you put together all these results, so this is far from to be so there is a huge gap to fulfill here. And let me go back to this result. So this is the result of Malikios, where it says that when you have n is a square phi number, and you just then you have so it just says that the tile spectral direction is true when you have just square phi number, and you can raise one of the power to 2, one of the exponents. So there is a simple observation that I would like to start here. So if you take any group and you take a subgroup and the coset representative of the subgroup, then it's a tile. And the so-called Coven-Meyerowitz conjecture states that there is no other type of tile when n is a square phi number, and then you take the cyclic group of order n. And obviously, so if you take a subgroup, then this is also a tile, but in this case, subgroups are also coset representatives. So and this is only called the Coven-Meyerowitz conjecture because they did not conjecture it. It probably first appeared in a blog of Tao, where he thought it would be interesting to investigate this problem, but it was actually solved there by Laba and Meyerowitz by some comments, and these comments rely on a strong result of Tiedemann. And but a complete proof first appeared in a paper of Xi. This is why this result is also mentioned here. So, but this is not true even in the case of ZP squared. So as I mentioned, a subgroup is also a tile, but in this case you have the unique non-trivial subgroup of order P, which is not a coset representative, obviously. So you can't have such a result in general, but you have to do something. So it's like, so this is the result of Coven and Meyerowitz. So they defined the two properties T1 and T2. So you take a function from the cyclic group to the natural numbers, and then you can define the mass polynomial, which is of this form. So think of it as just a characteristic function of a set, and then this is just the sum of some x to the k's. And this is not really a polynomial, but this is a polynomial in the polynomial in this quotient ring. So you have to factor out by this x to the n-1 because these are not integers. And there are two different properties. So S1, so what is the cardinality of S? So this is just the sum of these values, which coincide with the cardinality if it's just a characteristic function of a set. And this should be equal to the product of some primes. So and the condition for those primes is that the cyclotomic polynomial of I don't know, order p to the L should divide the mass polynomial. So if you have such a division, then you have to put a p here, and the product of these primes should be equal to the cardinality of S. And there is an even more sophisticated property, T2. So if you have a bunch of cyclotomic polynomials dividing the mass polynomial, then you need to have one specific cyclotomic polynomial. So you have to write here the product of these prime powers, and these prime powers should be co-prime. Okay, so and Coven-Meyerowitz proved that if a set, so or its characteristic function has the T1 and T2 property, then it's a tile. The reverse conjecture the reverse direction we don't know. So we can only prove that if you have a tile, then the T1 holds, but we don't know anything about T2, or we have some results on T2. And these two properties are very central because Laba also proved that if you have a set having these two properties, then it's also spectral. Okay, so what are the strategies to prove the spectral tile direction of the conjecture? So it's so if you have a finite cyclic group and you know that the conjecture holds for every subgroup of that, and then you could say something. So first of all, these properties are translation invariant, so you can assume that 0 is inside. I mean, the identity element of the group is inside is in T and in lambda, and you also have if T and lambda are unions of ZP cosets, so they are very well structured, then T is a tile. Obviously, P should divide the order of the group. And whenever T or lambda does not generate the group, then T is also a tile. So it's so these are possible ways of doing some kind of induction. So, but let me just go back to what I promised to you. So, what are the exponential functions here? The exponential functions are just irreducible one-dimensional representation of obviously of abelian groups. So you don't have larger dimensional irreducible representations. So this is just denoted by me by here G, and obviously two of them are orthogonal on T if you take the difference of G and H that are group elements, and you take the character, and you take this character sum, which is equals to this formula, and then it should be 0. This is the orthogonality. And there is a very natural way to think of a representation. This is just a composition of two functions, a projection and the faithful representation. So it just suggests that it is enough to understand the kernel of the faithful representations. So okay, so this is probably I shouldn't repeat, but if omega is a multiset, and what does it mean that phi n divides omega, so if faithful representation vanishes on the mass on the multiset, so it's equivalent to the cyclotomic polynomial of order n dividing the mass polynomial. So this is a theorem that we prove that in this case you can write omega as the weighted sum of characteristic functions of ZPI cosets, where pi runs through the divisors of n, prime divisors of n. And then, so this has been proved by Steinberger, which was pointed out for us by Isabella Laba, but we rediscovered it, and there is the major, I mean, so there is a consequence that we use, which we call the cube rule. And so if you have a multiset, then you take, then I would call a cuboid a Cartesian product. Okay, so n is a square free number here, so Zn can be written as the product of ZPIs. So you take two-element subsets of ZPIs, which are AGI, and you take the Cartesian product and you evaluate your function omega on the cuboid, but you add some kind of weights here. So there is a natural way to define Hamming distance on such a Cartesian product. So, and you fix the vertex and you take all the points of the cuboid of even Hamming distance, and you add them and you subtract all those which are of even, which are of odd distance. So the weight of these, and this should be 0. So this is the consequence of the assumption that phi n divides the mass polynomial of the weight function or the multiset. Okay, and how am I going to use it? So this is a very simple observation that if phi p divides the mass polynomial, then since this is an integer coefficient polynomial, so then p is going to divide the current of t, and there is some kind of an distributivity on the cosets as well. So, and how can you get the conclusion that phi p divides the mass polynomial? It's very easy. You have to pick two elements of in the spectrum that are of Hamming distance 1, and the only coordinate where they differ is this p coordinate. So, and you can use this observation indirectly. So it's so if p does not divide the coordinate of t, which is equal to the coordinate of lambda, then there is no such pair in lambda, and there is no such pair in t, because if t lambda is a spectral pair, then lambda t is also a spectral pair. So you can't have a pair of elements of Hamming distance p which differ in the p coordinate. So how are we going to use it? We are going to prove a result of Xi. I mean, not the entire result of Xi. So we are going to prove that if T is a spectral subset of ZPQR, where these are 3 different primes, and this is the extra assumption that I'm going to apply here. So the phi PQR, so this cyclotonic polynomial, I assume that divides the mass polynomial of T, then I will just prove that T is a tile. So how does this go? So assume that 2 of these primes PQR divides the coordinate of T. Then I project my set T to ZXY. So if it's just a simple cover, then the T is obviously a tie. If not, then there are 2 elements which are of Hamming distance 1, and they only differ in their, let's say, in the third coordinate. So it just, as I mentioned in the previous slide, it just simply means that the third coordinate, I mean Z, divides the coordinate of T. So the coordinate of T is divisible by X, Y, and Z. So it's P, Q, and R. So it's just the whole set. So, and what if this is not the case? Then I will try to explain something on the whiteboard. So then I only have at most one divisors of P, Q, and R. So I'm going to draw you a cube. So it's like, so let me say that this is the P direction, this is the Q direction, this is R direction. I'm going to assume that Q does not divide the coordinate of T, and R does not divide the coordinate of T either. So I have a point here. And I mentioned that if the set is the union of ZP cosets, then I'm done. So I need to have a point outside. And since Q and R does not divide the coordinate of T, I don't have a point here. So I have a point here, but all these are outside. So now I'm going to apply the cube rule. So I'm going to draw here another cube. So all the points that are of Hamming distance 1 from this point are outside. So then I need to have this point inside because the sum wouldn't be 0 otherwise. And if, let's say, Q is larger than 2, I mean, one of these primes are larger than 2, then I will get that this point is also inside my set. But then I find a pair of points which are of Hamming distance 1, and they only differ in their Q coordinates. So it will imply that the Q divides the coordinate of T, which is just a contradiction. Okay, so that's it. That's the proof for the result of Xi, and I don't know whether I do have a time to say something else as well, or do I have 5 more minutes? Or
yes, go ahead.
Yeah, okay. So I will say something quickly. So there is the recent result of Laba and Marshall. which is interesting. I mean, for me, it's a very interesting result because so it says that assume that S is a multiset, or let's just think of it as an S, and I have two conditions. So I have a divisibility condition and non-divisibility condition of a cyclic polynomial where N and P are co-prime and P is a prime. Then they prove that the coordinate of S is larger than P. So so they call it a theorem, and it's very easy to prove actually this theorem. But they use it to prove certain other important result on Favard length that I'm not really familiar of. I just read their paper, but I'm going to mention a proof here that uses our mode P technique. So it's just a very simple observation. So assume that phi and P divides the mass polynomial. So we just simply observe that in this case, phi n divides the mass polynomial on ZPX. So somehow you can apply the cube rule for any cube, but somehow this condition says that the cube rule will not be satisfied in Z, but it will be satisfied. But this condition said that it will be satisfied over ZP. So you take a cubit and then the positive, let's say the positive weights and the negative weights are different. So you have such a cubit because phi n does not divide the mass polynomial of S. But as I mentioned, this difference should be divisible by P. So the positive and the difference of the positive and negative weights are just at least P. So you have at least P elements of set. So you can prove actually much more than that in some specific cases. But in the past, so this is a very useful technique that we use in one of our results that are mentioned here for when we prove that the spectral type direction of the conjecture holds for ZPQRS, where PQRS are different primes. But in the past few days, I just realized that I have an even simpler proof for that. But the recently mentioned result is due to Kish, Malikios, myself, and Wieser. And we have a lemma there, which I can formulate in the following way. So the setting is exactly the same, and we actually prove that phi n P and phi n divides the mass polynomial is equivalent to the fact that the cube rule holds for every Zn coset. So you take the Zn coset, you take the intersection of S with this coset, and you can just simply define the cube rule there, and this will hold there. But you can say this lemma in a different way. So if phi n P divides the mass polynomial, then the following are equivalent. Phi n divides ms is equivalent to the cube rule holding on each Zn coset. And if this is not the case, if phi n does not divide ms, then the cube rule will hold on none of the Zn cosets. So, and then there is a very simple observation. If you have 0 points in a coset, then from your set, then actually the cube rule holds for that Zn coset, obviously. So you can't have such a situation. So on every Zn coset, you need to have an element of set, which is somehow a stronger statement that you can see here because you have just a coordinately statement here. It's a statement of the coordinate set, and I have some kind of structural results as well. Okay, so that's what I wanted to say. So thank you for the attention.